In this video, we will talk about linear discriminant analysis or LDA, which is also a very popular algorithm for classification. So in SVM, we saw that we wanted to maximize the margin width, which indirectly means finding W that best discriminates the projected nearest instances from the two classes. All right. We can say that SVM is sensitive to local conditions because interior points are not participating in building the decision boundary. All that the decision boundary cares is what are the nearest points and what is the margin width. Okay, so it's the support vectors that influence the direction of the highway. Interior points never participate in the construction of the highway. Okay, so the best way to introduce linear discriminant analysis or LDA is that we try to find W, okay, that best discriminates the overall distribution of the projected classes. SVM did not care about the distribution. We are only looking at the nearest instances to the decision boundary. Okay, but LDA takes the entire distribution of the classes into account in constructing the boundary. So to start off, let's say that our optimal W is parallel to x1. Here are the projections of all the points on W. Note that the original feature space is two-dimensional, consisting of x1 and x2. But once we take projections on W, these projections are one-dimensional because W is our new axis. Okay, we are talking in terms of W. Project everything, all the points on W and see where those shadows are on W. Okay, so now it is all in terms of W. Okay, now assuming normal distribution for these projections for the two classes. Okay, we can see how the distributions look like. So W discriminates the class distributions like this in this picture. So we came up with an arbitrary W. Right now it is parallel to x1 axis. Projected everything on W. Assuming normal distribution, we can plot the normal distributions on these based on these projections. So these projections will have some mean, some variance. Using those, I can plot normal distribution. And this is how it looks like. So W discriminates the two classes in this manner. Okay. And how these two classes look different or separate from each other depends on the direction of W. Because ultimately these are built on the projections on W. Okay. Here is another direction of W. Now we can see that the discrimination is much better. Yes. Once we derive the optimal direction W, we can get the decision boundary. Decision boundary has to be perpendicular to W. Okay, because if you remember the equation of decision boundary, we use W transpose x plus b equals 0, right? So W is the normal vector to the decision boundary, which is always perpendicular. But ultimately, we can work everything in terms of W. So the idea is to find the optimal W such that the projected distributions of the two classes are maximum discriminated or they are farthest apart. All right, so that's the goal of LDA. So let's say that the class labels are 0 and 1. Okay. Now in our original feature space, which is in two dimensions, we have x1 and x2 as the two features. Let's say that both classes follow bivariate normal distribution with their own means and covariance matrices. Because it's not univariate, right? Because there are two dimensions. There is x1 and x2. x1 and x2 follows bivariate normal distribution with mean, some mean, and some variance covariance matrix, and this is different for each class. Class 0 has its own bivariate normal distribution, class 1 has its own bivariate normal distribution. Okay, and please remember here the means are vectors, two-dimensional vectors. There will be an average x1 and average x2 for the mean. Okay, and variance covariance matrices would be 2 by 2 matrices for both classes. Now on the right hand side we have the scatter plot of the instances. Okay, now you can see that the means of the classes mu0 and mu1, and the covariances are sigma 0 and sigma 1. All right, and these are the means are two-dimensional vectors and sigmas are matrices, 2 by 2 matrices. Okay, now for a given vector w, we can take the projections of all the points on w. We have seen this before. Okay, this can be calculated using simple projection formula that we derived in vector algebra class. So from two-dimensional space x1 and x2, now I am working in one dimension, which is w. Everything is in terms of w. We have projected everything on w. Now we are looking at coordinates of all the points along the w axis. Okay. Yeah, so with these projections on w of both these classes, I can calculate the mean of the projections and the variance of the projections. Okay, so here are the original mean and variance. Actually, variance doesn't make sense in this picture, but I'm just saying that mean of class 0 is located here somewhere. Mean of class 1 is located somewhere here. And these are vectors because both the means will have some average x1 and average x2 for both classes. Okay. In the original distribution, these were the parameters of the bivariate normal for both classes. Along W, I have projected everything along W. Now the whole thing has become univariate. Okay, class 0 has become univariate, class 1 also has become univariate along W. On these projected data points, I can calculate the projections of the mean, and also I can calculate the standard deviation or variance of these projections. This is all univariate. Okay, so that's why you see mu0 dash and sigma 0 dash are scalars. They are not vectors because these are just simple mean and variance calculation on these projections. So I can calculate the projected mean and projected variance along W for both these classes. Okay, and these will be scalars. Now the task at hand is to find the optimal W, the direction of W, along which the projected distributions are farthest from each other. Okay, we want discrimination, right? So what is that W that ensures that the normal distributions based on the projections on W are farthest from each other? All right, so how to measure the separation of these distributions? Originally, Fisher proposed a statistic as a measure for the separation of the two classes. So let's get down to the math. Okay, we can calculate the projected means, which are simply the dot product of the original mean vectors and W hat. Okay, so these means are here. These are the original mean vectors. The mean of the projections or the projected mean is the shadow of these means on the W vector, right? How do you calculate the shadow or the projection? Using the projection formula, of course, right? So it's the dot product of mu0 on W. That is simply mu0 vector dot W hat. And the projection mu1 dash here will be the dot product of mu1 dot W hat. Okay. And we can calculate the projected variances. So once we have the projection, so all these instances will be able to project on W. After we get the projections, we can calculate the variance using the variance formula of univariate distribution. I'll explain the math a little bit in detail once we work out after this this slide. So please note that the projected means and the projected variances are just numbers, and they are not vectors or matrices. Okay, so the total variance in the data, irrespective of the class, is the pooled variance. Okay, so if I consider along W, I've got different points. I've got projections from class 1, I've got projections from class 0. The total variation in the whole data, irrespective of class, is the pooled variance, which is sigma 0 square plus sigma 1 square. Okay. Now at this point, we should pause and think what we are going to do next. This is the total variability in the data, irrespective of class. Okay. Did you pause? What did you find? Well, Fisher proposed that we maximize this ratio between the group variance and within the group variance. And remember this, we did the exact same thing during F test. Okay, I mean, it's the same person, right? Fisher gave us F test. Now this is Fisher's LDA. So if we want to maximize discrimination between the two classes, we want that the between group variance to be large relative to the within group variances. Okay, the numerator will increase when the class means are far from each other. Look at the numerator. So it's square of the difference between projected means. That's the between group variances. There are two groups. What is the total variation between the two groups? That is square of the difference between the projected means. If the two groups are far apart, then the between group variance would be high. Okay, and sigma 0 square is the within class 0 variance, sigma 1 square is the within class 1 variance. The total within the group variance is sigma 0 square plus sigma 1 square, right? So relative to the within group variance, how large is between group variance? Okay, and for maximum discrimination, we want the between group variance to be as high as possible. We want the classes to be far from each other. That means we want the separation between projected means to be as high as possible. And this is the exact same theme in F test as well. All right, hence this is called as Fisher's LDA. And he proposed this statistic. So we maximize the ratio of between group variance and within group variance. And to maximize this, we have an analytical solution to this. Okay, the optimal vector W. So we only care about the direction of W. We are not worried about the magnitude or length of W, right? We can scale it up and down, but once we decide on W, that will decide the hyperplane decision or the decision boundary. We are worried about the direction of W because the decision boundary will be perpendicular to W. Size of W doesn't matter. Okay, so the optimal W vector is proportional to this quantity right here. So that's the solution for the objective function. Okay. Next question is, once we got the optimal W, we can construct the decision boundary which is perpendicular to the W. But where do we put it? Right? We know that it will be perpendicular to W, but where do we put it? Do we put it here or here or here? So one good choice is to place it exactly in the middle of the projected means, right? So our decision boundary will be of the form W transpose X plus B equal to 0, correct? And I have put the unit vector of W here in this equation. Doesn't matter, right? Only what matters is the direction of W. because I can arbitrarily scale this equation by multiplying a scalar. It doesn't change the equation. Okay, so our decision boundary will be of this form, right? Remember that W is the perpendicular vector to the line. So that appears in the equation of the decision boundary. Okay, so if this is the equation of the decision boundary, what is B here? B is the constant. B represents the distance from origin to the decision boundary. Okay, remember the distance formula from origin to the to a particular line. So if W hat is a unit vector which is in this equation, then it will be B divided by 1 because the magnitude of the unit vector is 1. So distance from origin is B, okay, in this case. So if this is the decision boundary, and ideally we want to put it in exactly in the middle of the projected means, then what will be B? B will be simply the average of the projected means. So once we calculate the projected means, we already have solved for W analytically, and we just need to so we have the decision boundary with us. We know the W. B is given as half of sum of the projected means, so it's exactly between the projected means, and W gives the orientation of the decision boundary. B gives the location of the decision boundary relative to the origin, and that's it. So this is our decision boundary as per Fisher's LDA, linear discriminant analysis. Alright, so let's look at a quick implementation of linear discriminant analysis, or LDA, in Excel and then in Python. So here is the data set that I have. Class y equal to 1, I have 30 observations. For class y equal to 0, I have again 30 observations. And you can see the scatter plot here, right? So what does linear discriminant analysis do? It tries to find the direction W such that the projected distributions of these two classes are maximum apart, right? So right now, let's say our W is along x-axis. So theta is 0 degree. Theta is the angle that W makes with x-axis. Right now, let's say it is flat. And you can see these two distributions. Assuming normal distribution, you can see that these two distributions are very, very close. So x-axis is not a good discriminator. Okay, if we take W along x-axis, then that is not a good discriminator. So let's try to increase theta and realize what is happening. So the normal distributions that I have plotted here are basically the parameters of the normal distributions depend on the projections. So I have projected all the blue dots and orange dots on this W, and from these projections you have to calculate the projected mean, the projected variance, and then accordingly construct the normal distributions. Now the normal distributions look a little bit separate, right? So that's good, and I can keep this increasing this. There is serious performance lag, but that's okay. This is just for a visualization purpose. So at some point, for some value of W, these two distributions will have maximum separation. Now, how do we measure that separation? Fisher gave us that metric. Fisher said we have to maximize the ratio of between group variance to within group variance. All right. So let's see how we can calculate those. So these are my original data. There are 60 observations, 30 each. The original feature space is x1, x2, and I can calculate the means of the original data. So mean of class 1 will be a vector, right? Average of x1, average of x2. That's all there is. Similarly, I can calculate sigma of x1, sigma of x2. This whole thing applies to class y equal to 1. Similarly, for class y equal to 0, I can calculate where the center of the distribution is, right, for class 0. and accordingly I can calculate sigma. Ideally I should be calculating the variance covariance matrix, because this is just one part of it. It's just SD of x1 and x2. What about covariance? So I will come to that. So this is just I'm calculating sigmas, but ultimately I will be needing the full 2 by 2 covariance matrix, and I'll be using the means as is. Okay, all right. So what I can do is calculate the again, all of these will not be part of the actual solution. Actual solution is very easy. I'm just giving you more details so that you can visualize the whole thing. We can calculate the projections of all these instances on our W vector. Okay, and that is very easy. So on W, we just have to take the dot product. So x1, hold on. So this value that you are seeing is the unit vector along W. Okay, and projection will simply be dot product. What is the projection of this vector on W? It is this vector dot W hat, remember? So this is simply 21 times this plus 32 times this. That is what the projection is. This particular point number 1 in the original space was located at 21, 32, but right now I am considering the axis W. So along W, where it is situated at a distance 33.881 from origin. I'm measuring the distance or the location of this point along W, and this is where it is located at. Okay, similarly you can calculate projections or shadows of all the points on W. So this entire vector is the shadows or projections of class y equal to 1 on W. Okay, similarly I can calculate the projections of all these points which belong to class y equal to 0 on W. So I'm labeling them as W1 and W0. That means W0 means it's a series of projections of all the points from class 0, and these are the series of projections of all the points from class 1. Both are on W. Now this is now univariate. Okay, I'm only talking in terms of W now. Along W everything is univariate. This is just one dimensional observation for class 1 and for class 0. Now using this I can calculate mu1 sigma or mu1 variance, and using that I can create the normal distribution. So that is how I have created these normal distributions, which are based off of the projections on W for both classes. Okay, and I need to find out that W so that the normal distributions are maximum apart. Okay, so let's do that math in the next slide. And Fisher gave us the analytical formula. So steps are very easy. First of all, you have to calculate the variance covariance matrix of the two classes. We already calculated the sigmas, right? So we have to calculate the variances and covariances. So basically for class 0, you have to take variance of this, and then covariance of these two, and create that 2 by 2 matrix. Similarly for class 1, you can create that 2 by 2 variance covariance matrix. So these are the variance covariance matrix for the two classes. Next step is to calculate the pooled sigma. Pooled sigma is very easy. Just add these two, you get this. Just add the corresponding elements, you get this. Okay, that's the pooled sigma. Now let's talk about means. We already calculated the means of the original means or the center of distribution of the two classes. Then you calculate the difference of means, mu0 minus mu1. This is the difference. Okay, why I am doing this? Because in the analytical formula, the W is given as proportional to pooled sigma inverse times mu0 minus mu1. This is the analytical formula. You don't have to use optimization or solver or anything. If you have the covariance matrices handy and the means handy, then you can just use this to get the W in closed form. You don't have to use any solver. Alright, so I got mu0 minus mu1. I have the sigma pooled variance covariance matrix. Now using these two, I calculate W, direction of W. That is important. So I'm using the same formula. If you see, it's matrix multiplication of inverse of pooled variance covariance matrix times the difference of means. All right. So this is what I get. Now I can convert this to a unit vector. Just divide it by length. That's all. Okay, so I got my W. Now W gives me the orientation of the decision boundary. So going back here, if this is W, then my decision boundary will be oriented this way. It has to be perpendicular to W. But where do I put it? Here or here or here? Where? We said that ideally we want to put it in between, exactly in the middle of the projected means. Correct? So we have to just find out the middle of the projected means, and that is easy. So you have the projected means here calculated, right? So this is the mu0 vector. Project it on W. That will give you the projected mean of class 0. Projection is easy. Just take dot product of this dot. This is the W hat. So this dot this will give you the projection. Similarly, this dot this will give you the projection. These are the projected means. So visually speaking, what is it? 50 and 37, let's say. So along this line, you see a distribution of orange and distribution of blue. Mean of W, the blue ones, is one of them is 30, one of them is 50. So that's all. Yeah, I think the colors are reversed probably, but yeah. So calculation wise, that's what it is. Actually, I can verify. So I have to first match the W. Hold on. So what is the W? W is this. This is the optimal W, right? And I have calculated the angle at which angle corresponding to this W. That's easy because this is a unit vector. The component of unit vector along x-axis would be 1 times cos theta. This will be 1 times sin theta. So if this is cos theta, what is theta? Theta is cos inverse of this, which is 70, close to 71 degrees. So let me go to 71 degree. You can see the more appropriate thing. So 71 degree. Okay, this is where the maximum separation happens. So yeah, mu of this red one is at 37.1 and this one is 50.7. Okay, so class 1, I think class 1 is the orange one. It has to be higher, right? Oh, sorry, it's the opposite. Class 1 is the blue ones. So the mean is 37.10 and here the mean is 50.7 for class 0. Okay, so these two values I see here, 50 and 37. So if these are the projected means, okay, then I'll create a decision boundary that lies exactly between the projected means. So it will be situated exactly in the middle. So this will be half of this plus this. That's all. So between, so let's say this is 30 and this is 50. So my decision boundary will be in between these two. Again, this diagram gets a little distorted when I rotate it, so don't get confused. But the decision boundary will pass through the middle of these two projected means. Okay, and that will be at a distance close to 44 from origin. So along W, if you travel 44, distance 44, I'll get that decision boundary. So below that decision boundary, everything is blue. Above that decision boundary, everything is orange. That's all. All right. Okay, so once we get W, we can actually calculate the ratio of what was the between square variance and within between group variance and within group variance. What was the ratio? The ratio here is 4.611. How do you calculate these two? So between group variance is easy. It is the square of the difference of the projected means. Correct? So we have the projected means here. Take the difference, take square, you get the sigma square between. This is something that we want to maximize. We want the means, projected means, to be as far as possible. Then we have proper discrimination, right? And this should be maximized relative to the within group variance. If there is inherent variability in the data, then the within group variance will be high. So only maximizing numerator doesn't work. It has to dominate the within group variance. Then there is true discrimination. Okay. So for within group variance, the formula is the neat formula is W transpose sigma W. Okay. Where have you seen this formula before? We have seen this formula in Markovich portfolio variance formula. Correct. So you know why this happens, because there also we have when we calculate the variance, we calculate the variance of the portfolio return. Portfolio return is given as W1 x1 plus W2 x2, weighted average of asset returns, and then you take the variance, you get this same formula. So here also we are working with projections, right? You are taking projection of x1 x2 on W. So here also we are getting W1 x1 plus W2 x2. That's why we get this closed form formula. If you are not convinced with this, so this is neat. Get into the habit of using this formula for calculating projected variance. Okay. Original variance is sigma, but then if you calculate the variance along W, then you use this formula. This will give you the variance, total variance of the projections on W. Okay. We can verify this. So earlier we said, so right now this is optimal, right? So these are my projections of the two classes. This is the sigma of the projections. All I need to do is, let's see, sigma square plus sigma square, 40.13, that matches. So this is 70.89, right? I'm taking 71, so there is little bit of difference, but you can calculate within group variance by summing up the individual variances of the projections. That also works. Okay, so yeah, we got the solution, and this is the optimal direction, and this is where you need to have that decision boundary. Same thing you can obtain using solver if you want, but you don't have to, because we have the solution in analytical form. But you can do it. So basically you'll assume some random W with some seed values. Okay, and this is the unit vector. Sigma square between you can calculate. So taking this W and this unit vector, what will be my projected means, that you can calculate. Take the square of that, and sigma square within also you can calculate for this particular W. Okay, and then take the ratio and maximize it. Solver will give you the value for these. Okay, and it should match. This will match with this one, or this will match with this. Okay, so yeah, that's all for the Excel implementation. And by the way, don't get confused. So see, this W is proportional to this. This W is also proportional to this. There is a constant, there is a proportionality factor. So this has been scaled. This is a scaled version of this, but the direction would be same as confirmed by the unit vector. So from here I am calculating the unit vector. From here also I am calculating the unit vector. Both unit vectors are same. That means this and this are parallel. It's in the same direction. Only that this has been scaled. So that's fine. Alright, so
Yeah, so this is LDA implementation in Excel. Let's look at the implementation in Python. That should be real quick. So here is the Python notebook for LDA implementation. Now, when I'm importing the libraries, the only change that I did is from sklearn dot discriminant underscore analysis import linear discriminant analysis as LDA. So I'm giving a small alias so that it will be easier. So let me run this. Okay, now let's read the LDA file, CSV file. Looks good. Now here again I'm instantiating a model object from LDA class, and everything else is same. So here what I'm doing is W is equal to model dot coefficient. This is what we have done so far, right? But it might give us a scaled version of W, exactly how we saw in the Excel, right? So instead of that, so the direction of W is what is important. So what I'm doing is get the model dot coefficients and then normalize it. So divide it by numpy dot linear algebra norm of a vector. So this will give me the W vector. It could be scaled by any amount, I don't know, but normalize or standardize that by dividing it by the length of that vector. Okay, so this will give me the unit vector W. Now I can match with Excel whether it's correct or not. And similarly, whatever B is the coefficient, right? Whatever B is the constant or intercept. Now also normalize that using the same normalizing factor. So the entire W transpose X plus B is getting scaled up or down by this factor. So now W is a unit vector and B is whatever it is. So we can match the results. So let's print this. So we get this. Okay, and here I have put the screenshot of Excel results. Now you can see that W, well, it comes with negative sign, interesting, but the direction is the same. I mean, it will be 180 degree opposite of what we have here, but if you look at the orientation, it's the same, 0.3274 and 0.9449. And B here, which determines the location of the decision boundary, that's 43.924. So that's what it is. So that's all for LDA. And yeah, by the way, when you have the decision boundary, you can easily predict, right? Anything above W transpose X plus B would be +1, anything below would be 0, depending on how you have defined the classes on which side of the decision boundary. So that's all for LDA. Thanks.
So that's all for now. This is Satya from Peaks to Tales. Thanks for watching.